Okay, hello, assalamualaikum, and a very good morning, I presume. Okay, thank you for looking into this video. All right, now we will be discussing field effect transistors. All right, um, field effect transistor comes in several forms actually. Okay, in a junction field effect transistor, which we call the jfet. Okay, which we call the jfet, we actually have, okay, the control voltage, which is the gate. Okay, so we have the gate, right, which varies the depletion width of a reverse bias PN junction. Okay, so this depletion width will be changing, okay, due to the reverse bias, okay, on the PN junction itself. So we have the PN junction here, right? Now, a similar device results if the junction is replaced by a Schottky barrier. Typically, we call this a MESFET, okay, metal semiconductor field effect transistor, right? But alternatively, you can also use metal gate electrode that is separated from the semiconductor by an insulator. Okay, sometimes people call this the MESFET, but quite common we call this a MOSFET because we use an oxide layer as the insulator. Okay, so in previous sessions, okay, we've been discussing about PN junctions, right? So we found two dominant features. Okay, the injection of minority carriers with forward bias, okay, and with a variation of the depletion width with reverse bias. Okay, so these two PN junction properties are used in two types of transistors. The first one that we've covered is bipolar junction transistor, okay, as we've discussed before, right? So basically uses the injection of minority carriers across a forward bias junction. Okay, but here we are discussing, okay, the junction field effect transistor, okay, where it depends on control of a junction depletion width under reverse bias. Okay, so you're not talking about the minority carriers, but you are talking about the majority carriers. This is why we call it a unipolar transistor. Okay, because when you talk about the bipolar junction transistor as before, okay, we are mainly talking about the operation by the injection and collection of minority carriers. Okay, because both electrons and holes are important, that is why it is called bipolar. Okay, that's why it's called a bipolar transistor, right? However, okay, in this case, the field effect devices, okay, they are controlled by a voltage at the third terminal rather than by a current. So that's the main difference. Okay, now, so if we look at what we have here, okay, the jfet that we have here, right? Basically, we have a source, gate, and drain. Okay, so you are controlling everything with the gate, right? So it's a three-terminal device. Okay, source, gate, and drain, right? And the important feature is that current through the two terminals, which is the source and the drain, is controlled by small changes in the current or voltage at the third terminal, which is the gate. Okay, so basically you can control to amplify small AC signals or to switch the device and on and off state. Okay, so these two operations, which is amplification and switching, are the basis of quite a lot of electronic functions, right? So hopefully we get a foundation to understand both bipolar and field effect transistors, and you can compare the two. Okay, so I've already mentioned this, right? So in a jfet, the voltage variable depletion region width of a junction is used to control basically the cross-sectional area of the conducting channel, okay, which is around here. Okay, this is the conducting channel. All right, so the current flows through the n-type channel between the two p plus regions, okay, or the rich p regions. Okay, so a reverse bias between these p regions, all right, and the channel, okay, causes the depletion region to go into the n material. Therefore, the effective width of the channel can be restricted. Okay, you can fix the resistivity by doping, okay, and channel resistance can vary with the changes in the effective cross-sectional area actually. Okay, now electrons in the n-type channel drift, okay, from left to right. Okay, from the left all the way to the right. Okay, the end of the channel from which electron flow is called the source here, right? And the end towards which they flow to, okay, so they all go all the way to the drain. Okay, so electrons flow from the source to the drain. Okay, and these positive p regions, which is the red area here, are called the gates. So if the channel were p-type, holes would flow from source to drain. Okay, so it is common practice to actually connect the two gate regions electrically. Therefore, the voltage gate, or VG, refers to the potential from each gate to the source actually. Okay, now okay, since you add okay, now what we have here is we are increasing the drain source voltage. Okay, so here is only 1 volt, here is already 10 volts, and here is 20 volts. As you can see, the channel near the drain gets decreased, okay, gets smaller and smaller as you increase the drain voltage, or in other words, the drain current. Okay, initially when you increase the drain current, initially there is a current flow, okay, sorry, the drain voltage, initially there is a current flow and it goes linearly, right? But when you reach a certain pinch off, okay, alright, this is where you will start to see the current flowing to the drain starts to reduce until to a point it becomes to a saturated value. In other words, the current is no longer increasing with increasing drain voltage. Okay, it stays the same, right? So this is a point called pinch off, right? So we call this the saturated current after pinch off. Okay, but we will go through as we go along. Okay, at the moment the gate bias is set to -1, but we will walk through into when it is at 0 bias and when we do have a bias, and we see how this affects the source to drain or the channel. Okay, how this affects the channel, right? So here we have a jfet under a voltage. Okay, all right, now at 0 gate voltage, okay, as you increase VD, okay, or the drain voltage, right, you come up to a certain point where there is a pinch off, or in other words, the current stays the same, right? So initially it starts at 0 or at some value, okay, and then it increases, and then up to a point it becomes flat, right? So that would be your IV characteristic. Now if you then so this is what I'm talking about. Initially it is linear. Up to a certain value you have a pinch off where the current starts to slow down. Okay, after pinch off you call saturation. Okay, so this is where the current no longer increases with increasing voltage, right? Okay, now So as you see here, okay, VD much larger than VD saturation, which is here, saturation voltage. So at here, you see the pinch off is occurring already over here. Pinch off starts here, okay, when the saturation voltage, when you reach the saturation voltage, you start to have the pinch off at the end here, and then it will just have a linear current. Okay, the current doesn't change, right? Okay. Now, if you then put a negative bias on the gate, okay, so the gate, you have a negative bias here, it's -1. Okay, effectively what that is doing, it is, okay, bringing down the value of the saturation voltage. So it occurs at a much smaller current, okay, right, and a much smaller voltage, of course. Okay, it occurs here rather than here, right? So that's effectively why you are putting it. You want to increase the resistance of the channel and induce the pinch off at a low value of current, okay, because the depletion ranges are larger with negative gate voltage. The effective channel width is smaller, and so the resistance is higher in the low current range of the characteristic. Okay, so the IV, you can see the IV curve here. Okay, pinch off gets smaller, right? Okay, because beyond the pinch off voltage, the drain current is just controlled by the gate voltage. Okay, you vary the gate bias, okay, you can have amplification of an AC signal. Okay, right? Now, you can actually calculate this, right? But we'll go through first how, or we will see what is happening when you change the gate voltage, right? So changing the gate voltage, as you can already see, okay, at 0 volt, okay, it's like this. But when you have -1, right, it is becoming pinching off at an earlier stage. Okay, you can already see it is starting to pinch off already, right? Okay, so this is what you call the gate control. Okay, you control the resistance that I was saying just now. All right, so that pinch off occurs at a much earlier stage. Okay, here, 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 right? Okay, now you can calculate the channel resistance. All right, channel resistance is just rho L over A. L is the length, okay, it's the length between the source and the drain, basically. All right, A is the area, okay, and rho is just the resistivity, right? Okay, so these are just I mean, if you want to substitute, right, so you can get an equation like so, okay, where A is actually the channel depth, right? Okay, all right, now for a jfet, okay, under voltage, you can also calculate the saturation voltage. It's given by this equation, where, okay, whatever you get here, you must minus the built-in voltage and the gate voltage. Then only you know what your saturation drain voltage is. Okay, now it's quite important that you know these equations. Okay, before pinch off, you get it like this. Okay, all these you can calculate easily. In the linear region, it's just this, but in the saturation region, you have to take into account, okay, an extra term. Okay, 1/3 is just the basic, this one, right? But there's another 2/3 where so this part is due to the saturation area lah. Okay, right. So the maximum operating frequency, okay, this is defined as the frequency at which the jfet can no longer amplify the input signal lah. So the cut off lah, the cut off at where it works, basically. Okay, so this can be calculated as such, right? You can have all in the book, okay, how to calculate this, right? So I've shown you about this before.